Welcome. My name is Arias Castro. I'm in the math department here. Dave Donoho was my PhD advisor at Stanford, and it's an honor to introduce him here. So in brief, David Donoho is the Anne and Robert Bass Professor in Humanities and Sciences in the Department of Statistics at Stanford. He received his bachelor's in statistics from Princeton, where he worked with John Tukey, which really influenced his thinking. And later on, his PhD at Harvard with Peter Huber in robostatistics. After postdoc at MSRI, he was a faculty at Berkeley for about 5 or 6 years in the 80s, and then moved on to Stanford, where he is now. He has, well, many prizes. MacArthur Fellow, Siam Fellow, where actually received the John von Neumann Prize. The IMS Fellow, IMS is the Institute for Mathematical Statistics, just in case. What else? Member of the National Academy of Sciences here in the US, the American Academy of Arts and Sciences as well, and the foreign associate of the French Académie des Sciences. Okay, related to the talk today, Dave was one of the earliest proponents of sparse methods, with pioneering work in the recovery of sparse signals expressed in over-complete dictionaries, and such as basis pursuits in the 90s, and more recently, compressive sensing. For this method to work, the signal has to be sparse in a known basis, and or dictionary, and Dave has been at the forefront of basis and dictionary design, starting with wavelets in the 90s and new systems such as widgets, wedgelets, curvelets. So let's move on to the talk.
Eri, thank you very much for the overly kind introduction. The 4 co-authors listed on this talk, I think, symbolize what's coming together in the talk. Ian and I are statisticians who've worked in decision theory and in some way don't think of ourselves as information theorists. Andrea Montanari is in the EE department at Stanford, young rising star. And he's definitely making a lot of contributions to information theory. And Aryan Malecki just got his PhD at Stanford in EE. So there was a coming together in the project that I'm talking about between statistics and information theory, and I hope that that theme is somehow useful to you as we go through it. So what I plan to talk about today is to just give a concrete example of a recent advance in practical terms of compressed sensing so people can understand that this actually is useful in the real world. And then I'll talk about the role that theory has played in making that advance possible. Then I'd like to describe why the theory to date, which is largely based on ideas out of harmonic analysis and in any event math analysis, is incomplete and only gives us a partial picture of what we ought to be doing in compressed sensing. By bringing in information theory ideas, we get a much tighter, cleaner, and fuller picture that is precise and sort of tells us what the right algorithms are and so on. So I think information theory really contributes a lot to the story. Okay, so let's just see if I can jump ahead here. So everybody, at least in their lifetime, will be in an MRI scanner. It's very boring. And for people who haven't been yet, we hope in the future it will be for less time than it is today. The trends are going in that direction, and that's what this talk is about, reducing the amount of time that you have to spend in a scanner. There are other applications as well, but that will just be concrete with this specific one. And let's say you're talking about a child that has to sit in the scanner for 10 or 15 minutes. Well, they're going to ask their parents why they have to sit still for so long, because it must seem to them like an eternity. The mathematician's answer to that is, well, we have the fundamental theorem of linear algebra, which says there's so many pixels, so you have to make that many observations in some sense. So if it's a 1,000,000 pixel image, you have to make 1,000,000 measurements. And it just takes time for the machine to set up the fields to make all of those measurements by the appropriate magnetic field. But what compressed sensing offers is to get the same quality of results in much less time. So I'm going to tell you about a paper here. It's a collaboration between the MRI group and the EE department at Stanford, headed by John Pauly, and in particular graduate student Mickey Lustig that I co-advised to his thesis, and doctors at Stanford and UCSF working in pediatric radiology. So the basic issue of developing something in EE is not just have a paper in IEEE, IT, or SP, but actually do something out in the real world. In this particular case, what has happened is this flagship journal of standard of care, namely radiology, has published a paper saying that actually we can use this technique to speed up by a factor of 6.3 from the amount of time that was used in pediatric imagery before to what it can be used using the new technique. So it's a very specific deliverable that's being offered to a target audience of children who don't want to sit still in the scanner for very long. Now, the technique by which this was done was using all the standards of research in the field of radiology so as to convince the practitioners in that field that this should be done. First of all, we're going to have trained radiologists who work in this area all the time, look at images that are not identified as to the method of construction, and score them as to whether they're diagnostic and whether they give confidence. That's terms of art that are used in that specific field. And there was a full experimental design applied here where a variety of speed-ups were tried and algorithmic combinations were tried, and there are other things as well, like do you use receiver coils or do you set up the specific scans in a certain way. All those variations were tried and to make a complete experiment by the standards of the field. Pediatric MRI was the setting, and multi-site means sometimes we looked at knees and sometimes we looked at heads, etc. So the specific improvement that was being considered was parallel imaging, where there's, for example, you can achieve parallel imaging by having multiple receiver coils. A kind of helmet on the person would help to get you sort of antenna diversity, to use EE terminology. Do parallel imaging alone, do parallel imaging together with the kind of L1 minimization techniques that we'll talk about later in the talk. And what the radiologist agreed is that if we use the approach that we'll be talking about, we could do the 6.3 speed up. And in concrete terms, it was from about 8 minutes in the scanner to about 70 seconds. And you could argue that the key thing is to get down to about a minute. You could probably have a child be still and patient for about a minute. They can maybe be trained to do that, but 8 minutes is hard to do. And of course, there's lots of marketing collateral that I could show you of how there are non-cooperative subjects who, rambunctious little kids are wiggling around inside the scanner, and on a time scale of 8 minutes, you just can't collect enough consistent data to make a nice image of the kind that you're looking for. So the speed up from 8 minutes to 70 seconds is a material improvement. And it gets you past some kind of threshold of becoming a real application. So here's an example of if you just use parallel imaging alone with the standard algebraic reconstruction technique that they use, which is some kind of iterative linear algebra, as compared to a technique based on L1 penalization. The same data goes in, it's a different reconstruction algorithm, which is something we'll discuss a bit later. The key point is that there are various features that the radiologists would be interested in. This is their emphasis, and they would point out that as radiologists, they would much rather work with the image on the right than on the left, and that they would not consider the speed up if they had to use the image on the left. They would actually back off and go to a slower data acquisition in order to get the clarity. The reason is they're looking at subtle defects in bones and tissues, and they want to understand if there are, fissures or tears and things like that, and the noise and other artifacts that you see the other way are just not acceptable to them. Okay, why can this work? We started out saying that there was the, fundamental theorem of algebra that's a fundamental theorem of linear algebra, and now we're saying, no, well, in the last few years, people are getting around that. Obviously, the theorem has been true and will be true in the future, so what has changed? Well, people now understand that because of the great success of information theory and transferring all this image content all over the world, that you're able to realize that there's many fewer degrees of freedom, or much less entropy content, whatever language you choose to pick, in describing an image that anyone can understand. If it's visually comprehensible, it just doesn't take as many bits as it would nominally seem to require just from a count of pixels or voxels. And so since there's fewer than the number of nominal degrees of freedom, it just seems we must need fewer than the nominal number of measurements. And so morally, if there's really only, say, 10 to the 4 big wavelet coefficients in representing some image that we're planning to compress by, say, JPEG 2000, which uses wavelets, if we see there's only a smaller number of wavelet coefficients than the full extent of the image, then it seems like the number of measurements ought to be comparable to that and not to the full image extent. Okay, so that slogan is enough to kind of get you in the door with doctors, and they say, well, if you have the theory behind it, then we'll try it out. And a variety of papers have been published by this specific group, and specific applications were developed. And I think that they took a very smart approach, and it wouldn't have been my approach because I don't understand enough about the field, but as they explained it to me, I really understood something about how you deliver applications in the real world. In effect, what they did is they took applications that were out of reach to the current technologies, and they didn't just try to improve something that was already being delivered. They took stuff where the current technology just wasn't able to deliver something anyone could rely on, and show that they could deliver it by using these sorts of speed-ups. So as a simple example, you could consider single breath hold cardiac imaging. So basically, a person can hold their breath for about 18 heartbeats, according to these cardiologists, and then you can take data during that time because the rib cage won't be articulating, and that's all the data you're ever going to get. Everything that can be extracted out in that amount of time. If you have a fixed field strength for your MRI, you're not going to be able to change the magnets that you have. So there's really just a fixed amount of data. And the question is, what can you do with it? If you can push into a new territory and deliver a new application with the limited data that you have, then that would be something novel. So the single breath hold cardiac imaging, by using a combination of wavelet basis and that's then tensor producted with sinusoids in time, they were able to make actually movies of the beating heart while a person held their breath from this very limited amount of data. These were clear and acceptable to the practitioners. So these sorts of applications are things that they were able to demonstrate. Now, beyond those applications, there's the thought that, well, there are many other things one would like to do. An example would be molecular imaging, where per voxel you're getting not just an intensity, but actually full spectral information, for example, of various chemical species abundance per voxel. When you start thinking about doing that, you've got 3 dimensions plus a spectral dimension for the 4th one. Sometimes you have multiple spectral dimensions to worry about. So you get up into very high dimensional data sets which seem to have 10 to the 7th, 10 to the 8th metavoxels. And then the question, if you can get anywhere in that direction, it would be interesting in this field. And so the need for making progress in that way with not so many measurements is apparent. And these are the kinds of applications people would like to develop in this field. Now, in the specific applications that have been developed, there's a kind of question that's hanging around, which is, it's actually accepted now pretty much by practitioners in this area that compressed sensing has a role to play, and it could be an acceptable approach for some applications. On the other hand, the idea of making fewer measurements has been there for as long as there's been MRI, simply because the basic motivation is so clear. The length of time in the measurement is such a downer for so many patients. And people did try to do undersampling, and they did try to do things that are somehow cognate to what we're talking about later in the talk for quite some time, but they were never taken seriously. And it was always said that obviously this could never work. There's something fundamentally wrong with it. Shannon already showed us that. This was a typical kind of riposte that these guys got from referees, and I can cite chapter and verse because people came up to me and said that. Now, actually, Shannon never said any of this, but this is people channeling Shannon, or their weak understanding of what Shannon would think in a setting like this, because of course he's sometimes given credit for the sampling theorem that's also called Nyquist, Kotelnikov, whatever, and it's thought that somehow the Nyquist theorem says that you can't do compressed sensing and so on. So it was theory that made a lot of people believe that this could never work. And what broke the logjam is not that practitioners didn't believe in it. They thought they didn't have permission from us, broadly speaking. So when we, broadly speaking, started giving them permission, then they went to town and started doing all sorts of interesting experiments, somehow with permission, which meant grant money. Okay. So what theory could there be? I'm going to go very quickly over some conventional theory and then try to bring in the information theory side of the view. So some conventional theory would be, we'll look back at the fundamental theorem of linear algebra and we'll amend it in one way. We'll say, suppose we've got a system of linear equations that's underdetermined, but we know one extra thing, which is that the object of interest is sparse, namely the entries are 0 most places in the vector, and there's a relatively few non-zeros. That changes the game, because if the matrix is a generic one, then what will be the case is that provided the number of rows in the matrix is at least twice the number of non-zeros in the vector that we're interested in, we will be able to recover. And in signal processing, this was noticed by people at UCSD, by the way. Bhaskar Rao and Irina Gorodnitsky had a theorem to this effect in a paper in IEEE-SP in '96, but it could also be viewed as sort of a basic theorem of oriented matroid theory going back quite some distance, at least 40 years. In any event, this basic fact shows there is a role for sparsity to play. Now, if you start down that road, you come to the problem that finding sparse solutions is not a very convenient algorithmic approach. That finding the sparsest solution to a system of equations, which is what would be suggested to you by the previous slide, is going to be an NP-hard problem in general, because there's all sorts of things that in particular cases reduce to that. So various kinds of packing problems, knapsack problems, and so on. So we can't expect in general to be able to do that. But if the matrix is more than generic and in fact is random, so let's say has IID Gaussian entries, and we can talk later about how that could ever happen. But imagine we had a random system of equations and we continued with the motivation from that theorem that I just quoted, where if x0 has at most k non-zeros, where k is less than n, then the thing that would be suggested to you immediately by the sparsity approach is that you'd want to solve what we'll call the L0 problem of minimizing the number of non-zeros, or the size of support of the object that satisfies these equations. That's the thing that we cannot do in general because it's NP-hard. On the other hand, if we just change the 0 norm to the standard L1 norm, then we've got something that's actually a linear program, and you can consider that as a feasible problem to at least attack. The interesting thing is that often in the underdetermined case, these two problems have the same unique solution. It's more general than just in this particular case, but for this talk I'm just focusing on that case. There's a lot of literature on this. And the information theory community, I think, published quite a few of the main papers in this, so that not all of them are written by information theorists. For example, I had a paper in 2001 on this, but they were willing to publish it even though I don't think it was Shannonistically correct. Well, thank you. Okay, so so let me just say a little bit of what I mean by this sort of large system analysis, large system asymptotic analysis, which will be important for later. So we've got the degree of sparsity, the number of measurements, and the potential number of entries in the object we want to recover. And consider a proportional growth model where we consider a sequence of increasingly large systems, and we have parameters rho and delta. Rho is measuring how dense the vector is, and delta is measuring how underdetermined the problem is. This will give us a phase diagram in the unit square, where horizontal will be the amount of indeterminacy in the problem, and vertical will be a measure of sparsity or density in the vector. And it turns out that there's a threshold or phase transition that exists. There's a function you can derive by combinatorial geometry that marks a boundary in this diagram such that below the boundary, L1 gives the L0 solution, no matter what the actual non-zero entries in X are. And above that boundary, the two disagree, and they actually disagree in an extremely bad way. Okay, so this boundary is the continuous curve that's here, and if you do an empirical set of experiments mimicking what we've said on the previous slide, with, say, a system size of 400, and you have a varying amount of indeterminacy, so this is very, very underdetermined. So 1/10 as many measurements as observations that you could conceivably be making. And here is your measure of sparsity. So you're very sparse down here and fully dense up there. Then you see there's this boundary, and below here is where L1 will give the same solution as L0, and above there is where it won't. And that's in the asymptotic theory. In the n equals 400 experiments, if you're below here 90% or more of the time in all of our experiments at grid points down here, we saw success, and above here, 90% or more of the time we saw failure. Okay, so it's a specific phenomenon that occurs for the agreement of these two computational ideas. One, convex optimization, the other one, this combinatorial approach. Okay, so the takeaway message is if we have a random underdetermined system and a strictly sparse solution, we can find it by linear programming, and somehow by some combinatorial geometry I'm not going to tell you about, you can figure out exactly what the boundary is, which sort of tells you you can go right up to this boundary but not more. And that's the real fundamental limit for being able to use L1 to solve this problem. Otherwise you'd have to use something that's more computationally intricate. Okay, now there's another notion of sparsity which is more inclusive. What we've been talking about in the last few slides was strict sparsity. We said we have some guys that are non-zero, and then they can be anything, and then there's other guys that are strictly zero. But you can use various ways of measuring a weaker notion of sparsity in which none of the coefficients truly have to be non-zero, and what we prefer for this talk is to measure by weak LP norms or LP norms, where P is less than or equal to 1. As P goes to 0, it becomes more and more like just measuring the size of the support, but for any P between 0 and 1, it's asking for a certain amount of sparsity. And there's a variety of things in mathematical analysis where these come up naturally. So if we have a bounded variation function on the line, its wavelet coefficients are in weak L1/2. If it's on the square, its wavelet coefficients are in weak L1. If it's piecewise C2 away from C2 edges, sort of a cartoon model, then there's something called curvelet frames that you can use for representing. It's a kind of harmonic analysis for such objects that are good with edges. And then you get the coefficients in weak L2/3. So these sparsity models allow for a more robust model of sparsity than if you had the strict sparsity. And we could then talk about the original math that came together to show that even for this more robust notion of sparsity, that there was this compressed sensing phenomenon. So in that model, we would make measurements just the same, and there would be fewer measurements than there are potential entries where the object is non-zero. The geometry of it becomes the following, that up in big N space, we know this thing is in an LP ball. Knowing this underdetermined amount of information tells us that all we really know is we're in some slice of a given codimension up in high dimensions. We know we're somewhere in there, and we know we're also in a ball. And it would seem that's all we know, and because of that, we can't do much. But there's a little diagrammatic way to think of it. We've all been poisoned by Euclid to always think of balls as being round, and because of that, we think of all directions as being the same. Now, if we thought about the L1 ball or some other kind of ball that's more of the type that we're talking about, associated with sparsity, has a special relationship to the axes in that space. And so you see that there's a face structure that's associated here. And although it looks in this low-dimensional rendering that these are roughly about the same width in every direction, it gets really not that way when we go to high dimensions. And so there's a giant gap between these that emerges. I think in the volumic sense is the easiest way to see that, but that's not the relevant one for us. What's relevant for us is that if you look at a hyperplane slice up in high dimensional space, through this pair of objects, then the slice is going to, hit a big part of the sphere. In fact, it's going to have the same radius as the sphere itself, but it's going to hit a small part of the L1 ball. It's going to have a radius smaller than the sphere, and in fact smaller than what would not naturally be the radius of the L1 ball. And as the dimension goes up, that phenomenon is only going to increase. As a result, you can document this through what are called the Gelfand n-widths, and that's just a measure of the size of those slices. That slice that we depicted for the L2 ball is always of radius 1, as you could see in every dimension and codimension, but it's for the L1 ball, it's actually much smaller than that, and it goes down with the number of measurements we're making and only slowly up with the ambient dimension. So there's this amazing gap between these two in a geometric sense, and there's a variety of work that was suffered over in the late 70s through the mid-80s in order to document these kinds of phenomena. And then whatever was needed at the time that compressed sensing came together was sort of put together partially without using this and maybe not as elegantly as some of what was known by the best Banach spacers. But anyway, we had papers that were published in IEEE, IT, I guess they were submitted in 2004, maybe appeared in 2006, that developed estimates of this kind and had this full geometric point of view. The key point is that there's an estimate about how L1 minimization does in all of these cases to reconstruct the object that you're really looking for, and that n-width that we just measured on the previous slide and that we showed geometrically is the coefficient that appears right here. And so if to the extent that that n-width is small and we can document it and so on, then we know that L1 is going to give us a good reconstruction of the underlying object in this setting. So in order for it to be small, there's something we have to have control of the number of measurements, and we control the number of measurements relative to the dimension of the object that we're looking at. Okay? So that suggests that you can do something here. Okay, so let me now come to this talk. That's just all introductory. And let me comment on all of that literature, which has not really been information theoretically correct or motivated. There's sort of a theory side and an algorithm side. There's a lot of progress between 2004 and 2010, and the emphasis was on harmonic analysis and functional analysis tools. So, for example, Emmanuel Condez and Terry Tao did a lot of papers, and I think these are the most cited ones, developing a tool called RIP, which is using some basic properties coming out of sort of functional analysis viewpoint and so on. What you get out of that sort of the dominant, citationally dominant approach is qualitative bounds and order estimates, because that's the way those kind of analysts think. They don't need constants. They don't care about that much precision. They kind of say, okay, the rate is so good, we win, and then they'll go off to do something. If you're trying to deliver a real application, if a number like 6.3x actually speaks to you, then that's just absurd. I mean, no one is going to promise that they're going to get a kid, a decent way of getting an image taken in 70 seconds based on some Banach space bounds, right? So that previous literature is not really going to address that, and you would like to have precise rather than qualitative bounds to replace that theory. On the other hand, there's a lot of algorithmic work, and much progress was made in 2004 to 10, and the predominant emphasis in recent years has been on bringing ideas that are known in linear algebra and optimization to bear. For example, low complexity iterative algorithms, such as Nesterov's first order method. But the problem is that doesn't really connect with anything very quantitative either. You're kind of like working in the dark. Why are we doing this? There's some tricks that people know from another field, and this trick is better than the previous trick that was coming along, so on and so forth. So something else is really needed, and that's really to bring some information theory and math stat into the picture. So what I'd like to talk is how to get more quantitative precision and how to get fast algorithms in a very interconnected way that furthermore uses in a fundamental way a representation that was discovered in information theory and is really the tool to understand this. In order to lay this out, I have to be a little bit of a pedagogue here and mention things that many information theorists don't know about, and that's Minimax decision theory. So I'm just going to quickly motor through this, but before I do it, I should just say, hiding behind compressed sensing, there's a Minimax thing where there's sort of two players going on. There's nature, and there's the researcher or the person reconstructing. And nature is forced to have a sparse object, in some sense, by the constraints of this game. On the other hand, the researcher is forced to pick some low number of observations, for example, by choosing a format of matrix that has a certain number of rows that's less than the number of columns. So that's sort of and then all the bounds that exist are saying that no matter what nature does, as long as it's the underlying coefficients are pretty sparse, in some quantitative way that we're going to describe either by the number of non-zeros or LP norm, no matter what nature does, you're going to get a good result. That's a guarantee. You can take it to the bank. So Minimax decision theory is about telling people, like, there is some guarantee about this, and it's not like a modeling assumption that you may not like the model. You just describe the specific constraint, and you could go measure it on real data and maybe see if it fits. So it's not that inaccessible of an approach. Okay, so there is some Minimax component of the compressed sensing literature. Now I want to introduce an older idea called Minimax decision theory, which is the only way we can state the formulas we need to state. So basic result, this was in the 30s and 40s after the von Neumann and Borel basic theorem of game theory came out, then statisticians realized that it was possible to use this in a very fruitful way in statistics. And for example, while we knew that the mean was a good way to sort of estimate the population mean, so that's the empirical sample mean and the population mean, we didn't have a really good way to articulate why that was. One way is that it's Minimax, that if you look at all measurable procedures that are functions of the data, and if nature could pick any mean for the underlying mean in this normal problem, then if you play that two-person game, then there's a saddle point in pure strategies, and it's very clear what the statistician will do. We'll just play y bar in this case. And there's the details of how this works and so on. A key point is that you can work with a lot of problems that look very complicated, like they seem to have, high measurable functions of n variables, and then by various arguments, it's really scalar, and that's something that will come up in a minute. So if you can prove this in one dimension for a scalar input, then you've got it. Now, this was generalized in various ways, and it was pushed out to show things like you can have a locally asymptotic Minimax estimator for the proportion in Bernoulli trials, or for the CDF in IID trials, or for quantiles, other things. So there's a whole theory that was able to develop showing that lots of things we're used to as being pretty good ideas actually had an optimality theory behind them. But that's all apologetics, because we already knew the estimators, and we're just finding a reason to use what we already knew. A different stream was, let's design new stuff, like come up with a new Minimax problem and design new estimators that come out of it. So one is the bounded normal mean problem, where we have the mean between certain bounds. And we could define the Minimax risk to be min over functions of the data. This is scalar. Max over means that are bounded. Now, if you bound it, then the obvious estimate y is not going to be Minimax. Instead, it'll turn out that there's a specific nonlinear function of the data, which is Minimax. That nonlinear function depends on the boundedness constraint. And going through exactly how you construct that nonlinearity and come up with it is very elegant chapter in decision theory that requires understanding a lot of Bayesian decision theory as well. But you come up with a Minimax rule, which turns out to be a Bayes rule for a specific prior. The prior is going to be supported on this set, and it's going to randomly pick means in this set, and then there'll be a saddle point where nature picks the mean according to that distribution, and the statistician uses this nonlinearity. Other examples of constrained problems, you can play the sparse normal mean problem, getting closer to our story. So we can imagine that we have an observation which is distributed according to normal x comma 1, where x is random and x has some distribution which is unknown to us, but most realizations of x are 0. So that's a sparsity model. And so the fraction of time you can be non-zero is controlled by this parameter. And then there's a Minimax risk there. There's, again, a complicated nonlinear rule that one could try and characterize for this that I won't bother you with at the moment. But I should say, like, the details of this function of epsilon and so on are fully known. At the same time, we could consider a sparsity model based on LP norms and so on and so forth. And now, instead of x being 0 most of the time, it just has to be close to 0 in some LP mean sense. And then you can have Minimaxity with respect to that, which leads again to a certain implicit theory. This function is well understood. Now, for practical purposes, we would rather not have some very complicated implicit decision rule, so we could maybe restrict ourselves to decision rules that just fall within a certain class. In this case, it would be, this is soft thresholding, and then we could define Minimax threshold risk, not just the Minimax risk, by an equivalent Minimax formula, but now we're only going to optimize over nonlinearities that are in fact applying a threshold with some threshold, and we just optimize over threshold. We can do that in the sparse normal means problem, where you're 0 except epsilon of the time, or in the bounded Pith moment problem. We come up with a Minimax threshold, and this is all calculated and explicitly known. Okay, so now let's indicate what you can do with that detour from information theory. The first thing that I want to indicate is if we go back to that result on the phase transition phenomenon, I introduced there a function that I said derived out of computational geometry. And the arguments for that all simply involve Grassmannian angles and so on. And it seems extremely delicate and extremely special to high-dimensional geometry. But it turns out that there's an identity that between that and something that comes out of Minimax decision theory, which was certainly not suspected before this. Namely, if we took the Minimax threshold risk in the epsilon sparse normal mean problem, okay, I just spoke about that. So the researcher picks the threshold, and nature picks a distribution of the mean that places all but epsilon of the mass at the origin, and the rest of the mass can be somewhere else. And nature tries to hurt you as much as possible in mean square. You get this function, which is characterized. So here, there's this relationship between this complicated thing about this phase transition of L1 equals L0 and this thing coming out of Minimax decision theory. Kind of strange, but it's going to continue. So, I'm not even going to stop. Okay. Let's consider now the weak sparsity model. So there we have the same kind of setup we've been talking about. We consider for our reconstruction now not min L1, but L1 penalized least squares, which has been called Lasso, or in IEEE publications sometimes called basis pursuit. And we'll normalize the thing this way with averages rather than sums because it works better for the asymptotic regime we're doing. We'll measure MSE for our performance, and we'll use an asymptotic framework that's more fully worked out in a paper by Mosen Bayati and Andrea Montanari, that namely there is an asymptotic mean squared error of the lasso in this setting, and it depends on the amount of undersampling, the distribution of the coefficients, and the penalization factor. And so now we're going to talk about that asymptotic mean squared error. That's the object of interest. So if we suppose pth moment sparsity, then we can have a Minimax problem at the level of talking about the asymptotic mean squared error of the lasso. So here the statistician, nature chooses something to hurt the statistician or information theorist. The researcher chooses the parameter for penalization in the optimal way, and we're trying to get the best result. And we have an exact formula for that, where now what plays in is the Minimax threshold risk for the sparse mean problem where it's measured by LP sparsity. And okay, so on the left is this quantity describing a particular reconstruction formula and its large sample limit, and on the right is something out of the scalar decision theory problem where there is no n, it's just n is 1. And you can make all sorts of exact calculations of operating characteristics. There are many more formulas like this. You can get relationships, asymptotic mean squared error, as some variable goes to some limit. Say, for example, if the problem gets increasingly underdetermined, what will happen to the AMSE? It's going to blow up as we go towards more underdetermined according to a precise formula. And you can see this is the exact calculation. That's the asymptotic form, and you can see that this sort of phenomenon is happening. We can also deal with noise, where now the only difference from previous slides is we add, say, Gaussian noise, although Gaussianity is not necessary. And we can deal with the noise sensitivity coefficient, namely what's the mean squared error, the asymptotic mean squared error of the lasso, in this case where we have sigma squared now in the problem. So obviously it's harder as the noise goes up, noise in your measurements, so that's there. But then there's this noise sensitivity coefficient that scales with the noise. And that, again, exactly involves this Minimax threshold risk used in a slightly different way than we used it in the noiseless case. And we can calculate that noise sensitivity coefficient. This is in the same phase diagram as before. This is the degree of sparsity, going up here, and the degree of indeterminacy. That's the phase boundary. Above here, L1 is a really bad idea. Below here, this is the specific noise amplification factor expressed in log terms, calculated from this. Okay, so you can never, no matter what nature does to choose its distribution of non-zeros. It can never make your noise sensitivity bigger than what's indicated on these level lines, and we can characterize exactly what is nature's choice that makes your life maximally difficult. Okay, there are lots of other formulas like this and lots of other situations, and for time reasons I won't go all into that. But I want to talk in a bigger idea, how could any of this be true? Well, what is it? Well, what's really going on under here is something that should be of interest to information theorists, which is that there's a stochastic representation that says that what Lasso is doing in the large sample limit, well, this is kind of a heavyweight algorithm that does convex optimization applied to indirect measurements. There's all sorts of niceties about, gee, various matrices are not of full rank. How can you even do this? Da, da, da. Right? This is a trivial algorithm where we apply a scalar nonlinearity coordinate-wise to something that's direct measurement of the object that we want plus noise, where the noise is somehow implicit and the threshold is somehow implicit, but there's a specific calibration of these things. Now, this is all true, or it's like it's only rigorously proved, let's say, in the case where the measurement matrix A is Gaussian, but it's all been empirically checked for lots of other matrices. The Gaussian proof is in a paper by Yati and Montanari. Okay, this idea as a representation, at least to my knowledge, I only know of it from a paper by Guo and Verdu, where what they did is studied the replica formalism for spin glass modeling of various problems in, I guess, CDMA or some other kind of problem that you fellows work on. And in working out what replica formalism was saying, they said, gee, if this is all true, then it's saying that if you do the MAP estimator under some model, that it has some sort of representation where it's some kind of scalar nonlinearity applied to the object that you're interested in plus noise. And if you apply that thinking, you'll get straight to this. Okay. The difference is, I mean, they proved what they proved, which was a fact about a formalism, whereas what we're talking about is a very specific case of what you could call a kind of a big idea. And in this specific case, we're talking about the lasso, it's convex, there's all sorts of beautiful things going on, and it's rigorously true at the level of talking about all of these limits and things. Whereas other than that, what you can think of the Guo-Verdu idea is it's a fact about the replica formalism. It's rigorously true that it's about that, and then you would have to prove in any special case that it actually applies to your setting. But the key thing is, as soon as you know this representation, then all the formulas go through. And that's why you can get all these precise facts. So the things that people could not do when they were working from the math analysis point of view is they would never even dream something this ambitious could possibly be true. How can you say that, you know, you're doing this convex optimization method of reconstruction, underdetermined problem? How could that have anything in the world to do with direct measurement of the object that you have just with some noise? That's a crazy idea. Who would ever go there? Okay, so let's say what the insight is that you get from this that you also wouldn't suspect if you were coming from just the math idea. There were those two implicit functions, one about the threshold and one about the noise level. This is noise plus interference, or noise plus self-interference is what we're calling it. This depends on the how much indeterminacy you have and the object of interest, its distribution, and the penalization. If you reduce this then that number goes up. So what happens is undersampling is the same as adding this kind of interesting noise that's in the stochastic representation, wherever it comes from. It's kind of magic. Wherever it comes from, what undersampling appears is you never see in this representation, undersampling never causes this to be observed through some kind of matrix, even though that's what's happening out in the real world. It's causing the noise to get worse here. Kind of weird. And at the same time, reducing delta also effectively dilates F, so that the more you undersample, it makes the sparsity weaker. And those are just like theorems. It's an exact equivalence as soon as you accept the stochastic representation. Okay, so I'm basically out of time, but I didn't finish with the agenda that I wanted to go through, so you'll have to humor me for a minute. I was telling you that information theory has something to contribute at the theoretical level, but also has something to contribute at the algorithmic level. And because actually what we care about is fast algorithms for doing this. If people push these things into very ambitious large problem sizes, like, you know, volume imaging with spectroscopic data or something, then N gets very big, and you really can't do the general convex optimization, etc. So people want fast algorithms. And I don't have the time to go over exactly what people are considering, but let me just show you these quick equations. There's an iterative thresholding algorithm where we apply soft thresholding of a kind to an object, sort of you have a current estimate, a current residual, you take an adjoint. This is reminiscent of relaxation that I'm sure you've seen. And that's what people first tried, let's say 2004. And then the motivation for that was that you just have to apply A and A star. And some of the A's that we use, even though we've been talking about Gaussian matrices, actually we do it with things that can be computed much more rapidly. And so such algorithms could run fast. The problem is that unfortunately it seems to take many iterations to do that. AMP is an algorithm that we've been working on, and it has a correction term on iterative thresholding that's basically looking at the statistics of things at previous iterations and making a correction on the current one. And it's complete, like, why do we do that? What good is it? You know, etc. Well, one answer is you get theory out of it. Another answer is that this is the term that if you do it, it makes that Guo-Verdu idea apply here. If you do it, then suddenly that nonlinearity being applied to a scalar channel, etc., that's what happens by putting in that term. So probably in information theory is probably the only place that I could ever explain this term, but I don't have time to completely go into that. Let me just give an example what happens. This is traditional iterative soft thresholding, let's say 2004. Then FISTA is something that's using basically an adaptation of Nesterov's first order method. So that's circa 2008. AMP is using this idea that is fundamentally at some deepest level it's using information theory. And it looks like it instantly converges on this scale, and it's just because the other things are so abysmally slow in large problems. This is the sparsity level and how many measurements we're making and the size of the object. So if we change the plotting scale so that AMP looks more plausible, you see that it's using, I don't know, 40 iterations or something, by which time the other guys haven't even really gotten going. And, you know, there are particular studies of AMP against all the popular things. These were done in Arjan Malecki's thesis that he just got his Stanford PhD in November. So these are pretty much the up-to-date algorithms that we know. In some cases, those algorithms come close, but they're few and far between. In lots of cases, they just never even reach, after many iterations, anything like the performance that you can get with AMP practically instantly. And why is this? Well, because the statistical approach of putting in this little correction that doesn't come out of linear algebra, which is about making various kinds of correlations vanish, makes the key identity true, which is the stochastic representation. That's responsible for all the formulas that we saw. That's responsible for the algorithm working so fast. So conclusion, CS is a rapidly developing with hundreds of field with plenty of papers. The math analysis was very valuable for showing that it was qualitatively well-founded. I spoke about today the idea that you can get precise quantitative formulas that connect Minimax decision theory with CS, but the engine of that is not really the decision theory, it's really the stochastic representation. And the implication for the real world is that there is an algorithm that makes that stochastic representation be true for the algorithm, and that's what makes it really meaningful outside. It's a fast algorithm. It requires a constant number of iterations independent of dimension. I didn't go over this, but if you want to know how quickly AMP is going to converge, and you try to derive actually the coefficient of the exponential decay. The coefficient exactly has the Minimax threshold risk in it. It's just m of rho delta over delta. So if you're at rho delta in the plane, you take m of rho delta, divide by delta. That's the coefficient. So if that number is less than 1, you're converging exponentially fast. It happens if and only if you're below phase transition. So all this stuff sort of comes together in a nice way, and I think it's a nice story for IT because, let's say, speculative work in IT that's sort of at the level of what you might think of as, theoretical physics work. Like, we know there's some structure to all these calculations we're doing. It's suggesting if this is all true, then this thing behaves like such and such a channel. That representation here, we're seeing that it comes up as a real thing, and it's of quite use in the practical world. Thank you for your attention.